some. Here we are. So remember our last discussion about the full coupling elements that we find over here with different functionalities like cross-domain coupling elements, which couple different domains. Mechanical, hydraulic, or electrical, mechanical, etc. So we have here some sort of taxonomy which divides the different coupling elements, meaning single domain and cross domain, into energy storing, power conserving, and we looked at the power conserving transformers and generators last time with the different coupling principles, so meaning interchange of variables, and or just the transformation of efforts into efforts and flows into flows in reciprocal manner. So this was our discussion last time, and today I will have a short introduction of energy storage, storing transducers with capacitive principle and inductive principle. That's what we want to do. And then today, the main part is how to glue together all these elements in the network fashion, which is very important to design the overall models, which is also important to understand if you work with the professional tools, because there you see this interconnection is done not with this one graph language or the equivalent circuit language, but with other pictograms that sometimes not working. You should understand what's necessary about if you connect some elements that they are working and what are basically doing to do that. For us as control engineers, it's also important because later on we want to deduce some sort of differential equations and want to look at what we have if we do this non-Poisson modeling, which we discussed last time. So that's our story for today, with some examples. So at the very end, you should be capable to understand what a state-based model is and where it comes from, and what is meant with if Mr. Kluge says, well, it's they are the integrators which are responsible for this states, and or we start talk about the energy storages which are relevant for the states. We will have a more precise view. So basically, I can change it here to go over this. These are the discussions from last time, and understanding that a DC drive and also AC drives can be understood as more or less as transducers and their power generator principle. So now let's jump into energy storing transducers. Energy storing transducers are different in their function compared to the power conserving transducers. The main difference is that the energy storing principle cannot be separated from the transformation principle, and that's very important to understand that. And I will give you some examples in the sequel. So please take this as the main takeaway. We cannot subtract more or less the storing principle from the transducing principle. So that's different to what we've seen before. Remember, a typical gear, there's a storage also present if you have a mechanical gear because of the inertia of the gears itself. But we can separate the inertia problem or the inertia modeling from the transducing principle itself. It's this putting this as inertia elements or capacitors or one-graph capacitors into the overall structure. The very same applies for the dissipative elements. That's the second message. Energy storage transducers. For energy storage transducers, it's always the case that you can separate the dissipative elements from the transducing principle. That's always the case. So here is the very first example. There you see an electrodynamic transducer on the left-hand side, which is also some sort of a symbol which shows what happens. Now, let me explain this main idea. You have here a coil and here the piston which moves from left to right, and you know, if you apply a certain current or current flows through the coil, what happens? The magnet or the material moves inside of the magnetic coil. That's well known. And well, with that, so this is how loudspeakers are working, but also you can use this to actuate in a small version, for example, to introduce vibrations into mechanical objects. Well, we use it in experiments, for example, for have small scale movements, which can be very precise. You can buy this kind of a magnetic principle from the company PIs, the principal instruments, which is close by here in Karlsruhe, with which we work together. So they produce such things to actuate, for example, plates, mirrors, in whatever application you like. So very often in optical applications. So this is the very principle. You apply certain voltage, current flows through the coil, and this magnetic or magnetizable material moves into the coil. So we get some sort of force and velocity, and here we are with our force. Port 1 is the current voltage connection of these two. That's the first power pole, I times U, and the second port is described by the force, so the flow and the velocity as the effort value. And the coupling relation here, so if you're interested to understand the physics behind this, you find the introduction of this in the book of mechatronics elements. I think it's somewhere listed here, yeah, by Klaus Janček. This guy here from Dresden, sustainable mechatronics system. It's used. Well, the force is well, important to know. Obviously, if I move this part, this magnetic part, into the core, what happens with the self-inductance? It becomes larger. The more magnetic material is inside, the higher the inductance is. So obviously, the self-inductance, the storage, is somehow influencing completely the kind of how much force is produced. So one can say the storage principle, the self-inductance and the inductance of the entire thing, depends on the movement itself. And therefore, you cannot easily say, well, there's some storage, so magnetic storage, and some movement, and that's it. It's not like the case we looked at before. No, as you know, as you see, unfortunately, it's also nonlinear. You get the force based on the self-inductance, which obviously depends on the position, and the position perhaps might be oops, might be defined by the end of material. And as you see, the higher the current is, the higher the force is, unfortunately, where here it's a non-linear. This is perhaps the first interesting fact, and due to the fact that the magnetic material moves into the core, the self-inductance changes, and this is described by L effects. So if you know, if you have the R in between, you can describe this with your knowledge from the electrostatic way to describe the self-inductance. Well, mighty material core system, so it's not rocket science to describe this in that sense. Now let's look at the voltage side, which is also interesting. The voltage is induced when you move magnetic material into the coil. It's very law of inductance. And this depends obviously on the self-inductance, what you know. So the voltage induced is equal to L times the rate of change of the current, but also on the self-inductance principle. So the velocity enters the problem. It's not just an induction principle, self-induction principle, but also a movement principle. And again, you have this coupling between the storage principle and or the storage function and the way how it's transformed magnetically. These are very famous devices in some applications. Well, loudspeakers, yes, easy, but we use it as movement generators for small-scale movements, also in practice. And then you have to deal with this kind of coupling. Unfortunately, so in terms of pictograms, unfortunately, well, there is no norm either on the equivalent circuit side. You see something like this, nor on the bond graph side, due to the fact that we have some sort of coupling between flow and effort. Here we say some sort of gyrator principle, and what you have to do, you have to include here, and this is a mistake, copy-paste mistake. You put here inside the relations. So if you want to be precise, you put it there to understand how coupling is produced. So from the control engineering perspective, if you have such a coupler, you see it's a nonlinear behavior. Well, let's have a look at the second principle, which is capacitive. Similar situation. Now you have a plate capacitor with a movable plate on one side. So the movement here, this plate here can be moved. So perhaps we add this to understand the movement. Movable plate, and the right hand side can be from left to right. So obviously it is not allowed that it crashes to the plate on the left hand side, but usually the mechanical construction works as follows. On the movable plate also the string, so it will never hit the other plate. So what happens, plate capacitors work as follows. The closer the plates are, the higher the capacitance is, and these rules for reducing the capacitance of such a plate capacitor. So distance, plate area, surface area, and we have epsilon 0 and epsilon r and all those things. That's it. And if it's movable, so obviously there's a pulse produced if you charge on the left and right hand side. And by charging it, you will have a flow of current for the charge. In the same way, if you change the capacitance, you have voltage which changes clearly. So the charge remains the same, obviously. And if you get closer, you get this change of voltage. That's something you know from physics or high school. So and you have the very well, sometimes well-known coupling relations where the force is produced depending on the voltage squared, and it depends obviously on the specific construction C of X. We will look at in a second on some of these, and that's it. So it's a coupling principle where flow and effort relate, but the storage is included, so we cannot separate it completely. More evidently, you see it on the right-hand side here, the current in which flows depends obviously on the capacitor and the change of voltage in time, but also on a cross-coupling term, the effort and effort variance. Again, one can say it is more close to a gyrator, but I think it's somehow mysterious in that sense. So again, here the coupling relations should be put in there. Well, does anybody know what such a device is used in practice today? I have microphones. Yes, and microphones. Here, so might be there. Somewhere else. Also, as loudspeakers, also used. Interesting. But very much higher frequency is also used in other things. Obviously not here, but
maybe ultrasonic sensors. I'm not sure if we have
ultrasonic sensors. Depends. But ultrasonic sensors use piezoelectric effects usually to get these high frequencies. Interesting. Do you know? Yes. The accelerometers in UFO. Yes, accelerometers. Yeah, right. ODS, we talked about this, so microelectronic devices where you have an accelerometer where this happens. And in projecting devices, so there you have a laser which hits a mirror, and this mirror can rotate, tilt, and then project this laser beam somewhere. And very fast laser devices or projecting devices with a couple of beams projecting on this, the mirror that can project any image. With this, it can project, well, in heightened in light situation, etc. So it's very small, tiny device where this is used. That's one principle where we use such capacitive principle. So now here we see a couple of realizations, and this is copied out of his Klaus book. And the interesting, well, this is the very principle. Here you see C of X, to be precise, what you know from your lectures in electromagnetics. And here the plane might be rotatable, then it becomes even more complex for the calculations for the capacitance. So please, it's not necessary that you know how to get these formulae. So C of phi, well, this is something of electromagnetics, how to get this. Or a plate which are movable in X direction, something which rotatory capacitor. Then there exists something where the material moves into the capacitance. Well, on the armature gun geometries, we have similar things. This is a typical lift armature, U stator, E stator, and air gap stator, etc. So this is existing, and well, yeah, used in these microelectronic devices. And I came in contact with such a device, and it becomes so perhaps as a hint and important fact. For example, look at this one or that one. Here you have 1 over x squared. the force produced is 1 over x squared. The greater the distance is, the smaller the force is. That's perhaps the most important part. And if you look at this electromagnetic high-speed trains, they work exactly according to such a principle. So it's not always a small thing. So, and if you perhaps the Hyperloop guys who are working on producing such Hyperloop things. Well, here's the story how to model the coupling. Here, you get a certain force which pushes the train upwards to make it precise. And one principle to do that is you have here the magnet and here the coil, and then it moves up and down, and then you can flow forward by producing some sort of additional momentum. But lifting them up is exactly that principle. And the story I wanted to tell you, my first contact with that was during my PhD thesis, where, well, nobody talked about EVs, everybody talked about how to make combustion engines more efficient. And one fact is, what you know, like you have this inlet valves and outlet valves in a combustion chamber, and perhaps you know how such a classical combustion engine works. You have these kind of nozzles rotating and opening and closing the valves, and this is done at specific time instances when the airflow goes in and the used fuel air mixture is burned and afterwards goes out of the combustion chamber. And the interesting fact is sometimes it's important that the combustion chamber remains closed. The start of warming up phases, remember the EW problems in diesel engine gate. Well, that's exactly that. So when the car is warming up, you have different times when to open the inlet valve and when to open the outlet valve compared to the full high temperatures regime when the car drove already 100 kilometers or so on the highway. So the question was, can we adjust the timing of opening and closing the valve and to better make use of the fuel, to reduce the exhaust gas emissions, etc. And this was the question. And the idea from Benz at that time was to use inlet valves and outlet valves which are actuated this way. So remember today it's not present anymore, but at that time 8 cylinders, 2 valves make 60, opening and closing, electromagnets close by at 400 degrees Celsius, opening and closing, and now you can calculate the speed. You have to open and close this. Say such a classical combustion engine rotates with 6,000 RPM, so rounds per minute, means thousands per second, times 16,000 opening and closing per second. Now we're below the kilohertz range, or above the kilohertz range, and during this time you have to precisely position this part such that the valve does not smash into the entire engine. It should smoothly come into position. And this is a highly complex nonlinear control problem. And at that time, it was a nonlinear control problem at the one hand, and interesting enough, also a nonlinear problem because you have hot, very, very hot situation there. And also was difficult to implement with some control strategies. This is something where you say, okay, has never came into practice, unfortunately. So it worked, but it was too expensive at that time. And one realized the same strategy with the hydraulic mechanism and the mechanical mechanism, which has not the entire flexibility that is capable to do that. And if you don't control these valves, because this was the first idea, just had a feed-forward control, then these valves smash into the, well, today it's over, it's EV, but I found it very inspiring to see, well, the modeling part and in addition, the things. So here, additional structures, and on the right-hand side, PC5, that's it. So to pick it up, as you mentioned, ultrasonic devices are driven by piezoelectric effects. I did not put this here. It's similar. Again, we have a coupling, which is energy storage transducer. We cannot decouple the transducing principle. Again, it's not just used for producing ultrasonic sound, for example, for distance measurements and so, but also used for positioning of high precision positioning. For example, again, this company I mentioned produces these piezo drives for the positioning of mirrors for producing the next generation of embedded devices. So this is one of the major players for ASML or Zeiss or whatever. So therefore, very interesting and wonderful control problems. So that's the story. We have this basic elements, one ports, the two ports. To recap everything, we always find two kinds of storage principles, so capacitive and inductive. We will have usually coupling elements in our structure, and with these basic elements, we can produce any system. That's the message, the main takeaway. And that's why, after I realized this during my personal studies, I understood, okay, that's why control engineering is working with their principles, because you can always rely on these simple elements, and they behave always the same, and therefore we have the same structure. Well, one disclaimer. This is true for lump parameter system. So lump parameter system means that you have really crisp elements which behave according to localized elements. It's different if you look at the maximum equation. It's different if you look at the quantum equations, etc. So if you look at the lump parameter systems, you end up here. You can put this in such a framework. And the fascinating thing, last story, in that respect, we had a discussion with high professionals and modeling heat systems and also gas systems. So the transportation of hydrogen or natural gas and stuff. And this is a question today, for this energy transition question. And usually, if you look at the transportation of gas, you have to look at very difficult PDEs, partial differential equations, which you have to solve. So if you look at the girls and guys working with these gas systems, they study PDEs. And so solving PDEs is a tedious task. It takes time, and it's time consuming. It's difficult to find the right solver, etc. So it's really, really difficult. And today we have the question, we need these simulations to design, for example, the next district heating grid, or to design, for example, the hydrogen grid, which is now produced for the energy transition. So it's a question of ample importance of today. And it's possible
to describe these gas systems under certain assumptions which are okay with simple pi models, you know, from electrical transmission lines. And they are so simple that when we first discovered this, well, we needed a model for designing control strategies, and then, well, the PhD students designed this kind of model and realized, okay, under certain assumptions, we end up with a pi model, so no surprise at the very end, because it's very close to what we know from Maxwell's equations for the transportation of electrical energy over transmission lines. And we thought, yes, and somebody must have seen this in literature. We did a really vast literature review, and we did not know anything about this. Then we talked to very, very experts in that field, and they were surprised with what kind of precision such a system can be simulated in this case. And the interesting fact is this long parameter system helps us to design control strategies, and it also helps to do the grid design, for example, for such a gas system. So sometimes it's very helpful to do it in that way. So these are the key takeaways for that. It's non-causal, remember that. So we do not have a specific transportation of information with a direction, like in the Simulink block diagrams. There, we always have some sort of direction. It's more the informatics principle. You have somebody who sends the information, somebody who gets the information, and there the transformation, the direction is given. Here, energy can be exchanged from one system to another system. They are coupled by a force, and the only thing we did, we indicated this error in one graphs or remember that electrical networks, you do not see anything, just connections, just a line between the elements. This is the positive sign, that's it. So now the question which first appears, well, how do we glue together these different elements? How do we do a network analysis? Well, this is important in particular if we want to understand what happens if we want to reduce mathematical models at the very end. So we are interested in the mathematics, which are important for us as control engineers. And this is the step we want to do here. And also to understand what kind of mathematical object we have in our hands. I showed this last time, short glimpse, but today we want to understand it in more detail. And that's a question. And later on, we should understand what do we have here? What kind of object do we have to simulate? What kind of numerical solver do we need, for example? If you use MATLAB simulating and you click on simulate, well, always some sort of numerics is behind. And this kind of numerics, is it different for such kind of objects? And the answer is unfortunately yes. When we go to the MATLAB simulate service, yes. And we want to discuss how. Okay, so first, topological connections. The first thing which is perhaps interesting, if you have a body and you apply certain forces, you know the equilibrium of force law, which means that F2 minus F4 is equal to 0 and F3 minus F1 is equal to 0. So everything sums up. So the flows, the sum of flows on a body is equal to 0. So to make it precise, the sum of flows, this is something you know, right? The sum of flows is equal to 0, it's something you know as Kirchhoff's current law, right? Now let's have a look at the hydraulic system. So my garden watering system, everything which goes in goes out if you don't have holes somewhere in the pipes. So the sum of flows is equal. So again, F1 plus F2 minus F3 is equal to 0. Again, Kirchhoff's law, something you know. So this is something which we already know, and the link between so-called bonds is called a junction. So if you connect something, then we do a junction, and this junction is non-dissipative, non-storing. So an entire energy which goes in goes out, and an entire power which goes in goes out. Let's have a look here. If you multiply everything with the same speed, then well, obviously the power in is equal to the power out. Well, and usually we know that there are two Kirchhoff's laws. Remember, there is the voltage law and the current law, and the current law is what I've showed here. Just a second. And at the very end, therefore we talk about two types of junctions: the zero junctions, so-called nodes, where the flow sums up and the effort is equal, and so-called one junctions, which we depict in equivalent circuits usually as measures. The voltage or effort sums up to zero, but the flow is equal. These are the basic building blocks of every topological connection. So now the question.
Can you maybe go back one slide?
Yes.
So what's the difference between the force of the impulse flow and the hydraulic flow? So that you have to consider the direction of the impulse flow, but not the direction of the fluid flow.
Both cases you have.
Yeah, but in this case, F1 plus F2 are 3. But
Yes.
if you cancel out F1, for example, F2 and F4 are not equal to F3. Like you have to take the direction of the flow figured out.
Yeah, but here also, here everything which flows are in indicated by
Only the mathematical notion of direction rather than like the geometric direction.
okay.
But why does the impulse flow have 3 dimensions that order?
Okay. This is perhaps a little bit misleading. Well, if you to make it more precise, suppose we are here. You have two independent directions, well, so the y direction and the x direction. I think that's what you mean, right? And there you have a vector of flows, and we will look at this later on, where we see coupling of many vectors which are independent of each other. This also happens for pipe systems if they are not connected, but this is a little bit well, artificial, I would say. But you're right, you have to look whether some of the flows are independent from each other, they do not sum up, they have to be treated separately, and this is the case for the first one. So if you have two equations, where we have an equation for the flows in y direction, one for the x direction. That's it. But the story is always the same. You have these kind of Kirchhoff's laws in every domain. And I just wanted to show that's nothing what you learned during your studies in electrical engineering also applies in mechanical and hydraulics. And at the very end, you have two types of so-called junctions: the zero junction and the one junction. And the very definition of it is that the zero junction is the flow sums up, effort is equal, and the one junction, the effort sums up, but the flow is equal. And that we are used to work with equivalent circuits, where if you do, for example, nodal analysis, where you look at the Kirchhoff's laws of one node, then you draw into your pictures the direction by the way, it's important. At that point, you have to decide what kind of direction you count positively. The only thing is you should not mix everything up. So again, stay on the same sign convention. And then you find the nodes. And the interesting fact, the one junctions are not explicitly depicted in equivalent circuits. So remember there we depict method, or we depicted the one junction where this effort sums up as a mesh when you know from mesh analysis from the linear equivalent circuit for networks from the first semester. I think. Yes.
We just close the loop over.
Yes. Yeah, that's exactly what I mean. So if you say, okay, let's have a look at all elements in one loop. So look at one loop. And but if you have a different notation, you depict these two rules, F1 rule and flow rule, by means in bar graphs as a so-called zero junction, and it was very innovative to say, hey, let's take a zero in between, and say, okay, here we are the zero junction flow sums up. F1, F3, F2, but effort is equal. So here we can say E1 is equal to E2 is equal to E3. And the zero junction means F1 is equal to F2 plus F3. So due to the sign convention, which is now encoded in the bond graph signs. Same on the right-hand side, but now we have the zero junction here and the one junction there. Here, effort sums up, and in the sense that E1 is equal to E2, sorry, plus E3. On the other hand, the flows are equal. And that's what exactly you are doing if you're doing loop analysis, if you're doing mesh analysis in linear electrical networks. If you remember the two strategies, you draw the loops and then, oh, I count the same current and you can do the calculation. You have the very same for nodal analysis. You have the very same, you look at this Kirchhoff's current laws. Well, here's explicitly represented the two laws. There, in the equivalent circuit notation, you have it implicitly due to the meshes. Well, on the other side, as a key takeaway, there are always two topological groups. We find there are two topological groups, like the zero and the one junction representing these things. So what we have to do is, if you are new in the domain, you should look for this. It helps. Now we want to learn a little bit how to construct the entire equivalent circuit if we have a schematic. So in electric writing is easy because the equivalent circuit is given because it's an equivalent circuit. So we want to learn the strategies. This is not because I want to force you to learn to transform everything into equivalent circuits or into bar graph notation. It's just to help you to understand what's happening. So what's going on. So you will never, in practice, do bar graphs. No. It's just for checking whether you understood everything in terms of how the interconnection works, what's the basic principle behind. So my examples are always very, very small, also in the exam, but you will understand what's behind of the story, and you will understand the various tools like Daimler, Simscape, etc., what they are calculating if they are connecting different elements. So if you find something which is today, if I look in the various tools, they are much more close to what we know from equivalent circuits technology. It's interesting. Well, we put a different picture to it, because mechanical engineers here or electrical engineers, you should know this, it's important. Yeah, it's the truth. I had a course for senior engineers coming from mechanical engineering training. And they should shift more to electrical side because mechanical engineering. So they learn a lot about combustion engines, and they should be reoriented into system dynamics, etc. And there was one colleague, already 50 years old, 51, 52 or so, I don't know anymore, so as old as I am. At the beginning of the course, he said, well, the most hated lectures I had during my studies was electrical engineering and control engineering. I thought, oh, this is wonderful. This would be nice, but at the very end, he laughed it, I hope. So what I show you next are two strategies how to systematically derive such equivalent circuits based on schematics. This is not a problem for electrical engineers for electrical schematics, but this might be a problem for transferring mechanical object into an equivalent circuit or an hydraulic system into an equivalent circuit, etc. So we do it with mechanical things, but we will do a lot of examples during the exercise lectures of Mr. Isler, and we do the very same with the bond graph. And again, as a disclaimer, it's just for understanding the principles and doing the variant analysis. So please follow these steps. Really, really important attention. I always give you examples which are a little bit, well, they seem to be easy. They are small, they seem to be easy, but they are always somehow breaking some sort of, well, intuition. And if you do not follow these rules or these steps, but if you say it's not a rule, it's a stepwise procedure, very often students fail. So if you look in particular in the exam, you have a small tiny example and you say, hey, it seems so simple, and you draw it and I say, please have a look at this. There might be a problem. Then, okay, my intuition says, and this intuition often is wrong at that point. So, remove that one. Very same happens for the bond graph. By the way, also a important notice is if you construct bond graphs, sometimes electrical engineers feel more comfortable to first produce the equivalent circuit and then produce the bond graph. Well, some of you are very well trained at the very end and can produce the bond graph directly, but it's not a problem. It depends on you. You do what you want. If I ask for the bond graph, you can, as an intermediate step, first construct the equivalent circuit. So, well, what are the steps? First, draw the domain-specific graphical representation denoting the different domains. So you should be careful, you should take care of the different domains. Okay, that's clear. Then you define generalized value in network variables. So that's the very same, you know, from electrical engineering network analysis. You wrote in these lectures, we wrote at every branch, the current and voltages. Here it's the very same. Then you determine the generalized network elements. This corresponds, by the way, to the idealization step, where you say, oh, okay, I take a linear dissonant element, or a nonlinear capacitor, or whatever. And then you just simply apply topological rules. Important on places with equal potential, including equal to 0 as sign and node. So please do that. Even if it seems to be overly complex, it's not. It's helping you to put all elements in between. And then please put the elements in between in accordance with their position in the original diagram. And this sometimes seems a little bit strange. Some important note or remark is masses, so mechanical masses, are usually connected to ground. Why? Because if you remember, a mass, a movable mass, so kinetic energy means they can be represented by a capacitor, right? A capacitor has intuitively two wires. The mass is one point mass, for example. Where's the second point? Where's the second third? And the answer is very simple, but it's somehow hidden a bit, because the mechanical engineers learned in the very first semesters to define at the very beginning always their inertial system. Say, this is the star, sometimes it's the Earth, which does not move, which is not accelerated, and they reference everything to that. And we have to do the very same. Electrical engineers do the same by defining and referencing everything with respect to ground. That's what I'm saying. And this is something you do, and that's also the same thing you do. And you get really in a problem if you take masses with different difference points. So it's always a good idea to reference everything to the same point, whatever it is. And my advice is, please reference everything to the ground, to one non-movable plate or whatever. So to a inertial system, so the ground. That's the message. And this makes the problem because then every capacitor is always connected to the ground. This seems a little bit strange if you look at mechanical objects. So let's have a look at one example, and then we see that if you do this the first time, you feel uncomfortable with that. But it brings me later on with to show you. And here is something which I show in mechatronics engineering, also in the mechatronic systems lecture. So it's the very same example. What is it? Today we have a so-called damping system, which is needed for damping down oscillations. Why? Well, what happens if you produce power by means of a steam power plant? And then the object works as follows. You have the rotor and the turbine. So steam flows through the turbine rotates. Then you have the piston that rotates, and at the very end you find the generator, right? So what happens if you switch on your oven to cook a pizza or whatever? Well, there's a certain amount of power consumed, dissipated, and what happens with your generator? This is a question. If you switch on the oven, what happens with the generator?
The force of the floor. This is more for needed to rotate the car.
Okay, so does it speed up or slow down?
Slow down.
It slows down, right? So if you switch on, if you cook a pizza, you slow down the generator. Well, next, a little bit about signal processing or signal analysis. You switch the oven on with a jump, right? So from 0, no current, or say 5 amperes, so just on. If you look at the frequency spectrum of a jump, what does it mean? How is the amplitude of the frequency is produced by a jump? How does it look like? So velocity. So off, on, just the step. You remember this? Yes.
Should be one of the so just higher.
Looks, well, if you have set and you do the Fourier analysis of the step, what do you get? It's like a thing, sig, so sine over x, right? Sine over omega. So it's a function which looks like this, right? So you have almost every frequency in the spectrum with different amplitudes. Now, here comes the problem. What happens if you have a shaft which is rotating? You have here a force. So I try to typically this. This is my very example over the last 10 years. You bend it. Here I hold it, and here I bend it. Because and now the bending is at different frequencies, and you see the problem. It radius of the wire. So this is the difficulty for mechanical engineers, because they know from material science that dynamic forces are much more difficult, much more problematic than a static force. But one bending and then holding it is different to back and forth and yes, I saw. And you know this from this nice little clips when playing around and moving forward, backward, and after a while. And so I like this to play with this. So, and this happens in practice. So if you sit on and cook pizza, the shaft begins to oscillate. These oscillations are not wonderful for the mechanical engineers because they need material to circulate. So what we can do is we can damp down these oscillations. And this is done in practice with a mechanical anti-oscillator. So which is given here. It's a mass damping system. It looks like this. Yeah, I have to show you. Yeah, here the shaft, and around it you find a rotating mass attached with springs. So if it's rotating and stationary, it rotates with it. But if you are oscillating fast and you have a movable mass outside, which is heavy, well, you have inertia outside, it rotates and gives a counter force. That is the principle behind it. So, and you see it here. Here's the picture in X direction, and there you have cut over the entire. Here is the shaft, which moves, which rotates. Here are the strings attached to it. And with that, we can reduce your pizza problem, so to say. And what we want to do with this simple example is we want to analyze it with electrical engineering methods. For mechanical engineers, it's not nice because this is oscillation theory. They usually do not like this because it's mathematics and well, we have to calculate differential equations and that. And I want to show you this is a wonderful structure to see what happens, and you see those structures which you might have heard of before. Additional elements, of course, the shaft is somehow positioned with a certain bearing, which produce friction. So we have friction here. You know, usually the shaft is not fully aligned. So the shaft of the generator and the turbine. So you need something in between, which is a flexible coupling, and that's it. I leave the generator out because I just want to show you the mechanical example. Now, let's do the first step, the very first step. So the main specific graphical representation is already given. So this is this picture. It's somehow some sort of abstraction of the real world mechanical object. It's not a fully, well, computer-aided design thing. No, it's just somehow abstracted. This is the first step, what you usually do. So if you look at the robot, you know, look at the particular structure, you just abstract joints and arm movements, etc. So that's it. Let's give it here. Next, by the way, it's very typical. Sometimes you have some velocities, so angular velocities attached, but some are still missing. So first step towards that is to introduce the flows and effort variables, and that's what I did here, given with the torque variables M1, M2, M3, M4, and also I introduced a couple of velocities like omega 1, omega 2, which is there, and omega v, which is the velocity towards the generator, and omega 3 over here, and I torque, which is the produced torque by the hot steam of the turbine. So I reduced everything to the mechanical object. Then determine generalized network variables, already done, and determine generalized network elements for springs, masses, and dampers. That's the next step always. Well, the turbine, well, to boil it down, can be replaced by means of some sort of rotational inertia. That's it. And then I have it. The bearing is something like a resistive element, right? So there we have a resistor. And there the flexible coupling, well, in practice it's some sort of difficult nonlinear material, but let's try to represent it by a London spring. So easily. Again, we have springs here in between. So remember our picture here. Here's the shaft, the interior, and the outside ring somehow is somehow connected via these springs to the shaft in the middle. And last but not least, again, a bearing which somehow produces friction. And we use here a simple friction representation. That's it. And last but not least, the inertia of the outer ring has also to be represented. Okay, yeah.
Why is it not necessary to choose also the velocity of the steam?
Of what?
The steam outside of the steam, like what?
Yes. You can, of course. I was, well, at that point, the velocity of the steam.
And I'm just wondering how I will be able to convert it if I don't have the velocity.
Yes, that's right. Well, I was here. Usually, if I want to represent it correctly, I need a coupling element and to right. I just wanted to make the example as easy as possible. So you're right. If I want to represent it correctly, I need a coupling element in between, and there I need a velocity and the torque, and I boil it down to the torque. It's a torque producer, and because the velocity is not so important, we have so much flow, that's sufficient. On the right hand side, I put it so it's not very consistent, so to say. But for me, it's more to show how it works. Okay. Yeah, that's it. And now we follow the next step, which means that to every torque, to every node which we find, to every position between these different elements which we find here in the histogram, we have to produce nodes where we have a sum of flows and perhaps efforts later on. So what are defining the efforts? For every effort, we need a node. Here, one effort, there one, and there one, and that's it. And the interior is given by omega 2. So that's what can be done. Also, you can introduce as much efforts as you want. At the very end, you will connect them and then cancel them out during the entire procedure. Yes.
What exactly they want to do for the mass?
It's a mass, yes. It's a mass. So Well, perhaps it's easier to see it here. J1 or what do you mean? J4 and
Or J1, are they just mass?
these are the masses of the shaft on the one hand. So you have the shaft on the left-hand side, which is J2, perhaps, and the shaft on the right-hand side, which is J3, and the outer ring, going back here, this corresponds to the mass of which is outside J4. And with that, now I define nodes, which is given here. I try to attach to every position nodes. Node 1 is given here. So corresponding to omega 1, a node corresponding to omega 3 and omega 2, and then. Well, with that, I just put node 1, 2, and 3 in the diagram. So here, node 1, there, node 2, and somewhere over here, well, you can do it a different way, node 3. And there's something missing. We need a node with the zero potential. So the reference point is also needed. So as you know from electrical engineering, I put here the ground somewhere. And this is node 0. And to make my drawing a little bit easier, I put node 0 also here. So at both sides you find the ground. Well, now what we do is we try to attach the different elements between these nodes. So the first thing, your question, well, we have a somehow torque producer, which is the turbine, and I modeled it as just a simple constant torque producer. And this torque producer, what is it in equivalent circuit notation? Just a torque producer, an element which produces.
If we want to have the torque as a flow variable, it's a current source.
It's a current source, so it's some sort of current source. So what we find here is a current source which produces the respective current. And then next, let's have a look at the first bearing. So back and forth between these two slides, sorry for that. Here the first bearing somehow is modeled by means of friction. Friction is what in equivalent circuit notation? It's a question, yes? Exactly, the resistor. So, and now the question, if the node 1 is velocity 1, so back here, where does the bearing has a second reference point or a second connection to? So there's a shaft rotating inside the bearings. So you have these balls in between and producing forces to ground, exactly. So we have a connection to ground here. Okay, and of course you have to define some sort of element dr1 to be clear. Okay, then remember we have shaft 1 left-hand side turbine, shaft 2 right-hand side close to the generator, and in between we have this flexible coupling modeled as string. So what is a string in equivalent circuit notation? Do you remember that? No idea. Spring is, yes. No, exactly opposite. So 50% chance always. Okay, so we put here
a inductance in between, which we find here. And we know that's 1 over KR1 as element. If we know the spring constant K, then the inverse of it is the inductance constant for the element. Now, attached to node 1 is also the inertia of the shaft, right? So back to our picture. Here's the inertia of the shaft, J2. So we need to connect J2 as a capacitor to what? To the ground, right? So I do it here and leave some space because we need room for others. It's connected here, and there we find J2. Now, on the right-hand side, we have the second shaft. Again, it's a capacitor connected to the ground. So it looks like this. It's J3. Now the important thing comes how everything is glued to the bearing is there's something missing, I think. No, it's okay. So there's a second bearing on the right-hand side. And we need, let's have a look here. This bearing on the right-hand side is over here. Again, it's connected to the ground via resistor, as he mentioned. It's from node 2 to the ground. Oops, sorry, back. And this is corresponding to DR2. Now, the last element is following, and 3 is representing velocity or angular velocity omega 3. So we are here. So it's the velocity of the outer ring. In between the ring and the shaft, we find these. We find these springs over there. So we have to model the springs again as a inductor and the self-inductance, and the outer ring again as a capacitor as before. So we find the following in our equivalent circuit scheme. We find the inductor over here and a capacitor which fits to our ground, and 1 over KR2. At that point, you're ready. It's fine. And last but not least, the node 2 is the node where the generator is attached to. I just want to make it here. We find then I write it down as follows: generator. I don't want to model this, therefore I'll do. Now, it looks a little bit strange because we are not used to draw down such a and depict a equivalent circuit that way, but it helps to put your positions of omegas, the nodes at that position, which help you to get the topological structure still. They are there, the ones. Yes.
It's J1 doesn't do it in source.
What?
J1, the first one.
J1, the first, somehow missing. That's right. It's missing in my notes. Also, you're right. J1 should be included in J2, so we can do it the following way. Sorry. Over here, J1. Okay, so with that,
we're ready, and now let's rearrange everything a little bit, so that it looks like a Berlin circuit genome, and then it looks like this. Hopefully J1 is here, yes. It's just, well, moving everything a little bit in the way we were used to. That's all. And the interesting fact is, here you find your source, there the generator is attached to, and here we find J1, J2, as described before. And I think I made a mistake in the picture. I forgot to write down 1 over dr. Yes. So here it should be 1 over, and where's the second? Ah, yeah, 1 over dr. Okay, so now let's have a look at the final result. These J's represent the shaft. There we have the shaft on the right side. Here, the outer ring, and the bearings over there and there. The interesting fact, if you look at this spring damper system, so the ring around this, you can find it here. Exactly. This is J4 and the springs. So, just for you, if you look at such an element, of course, there's friction again, and I did not know the friction. But if you look at this, what is it? A inductance and a capacitor in serial image. You should know that from the electrical. Resonance circuit. The resonance circuit. So what happens if you exactly hit the resonance of the electromechanical material? Electrically speaking, if you find exactly the resonance, if the frequency here at MB or your node 2 is oscillating at the resonance frequency, what happens electrically?
I think the electric resistance is smaller.
It should be small, exactly. It's
So
not.
we kind of have a short circuit.
Well, short circuit, it's cancelled out, right? Because it flows all the energy which is resonating there flows to ground.
Yes, yeah, but only for damping. If you only want to damp the high frequency, we don't need this damper.
Exactly. That's true. So typically, what we have here for electrical engineers, it's not so surprising. It's some sort of, well, generally speaking, some sort of filter, isn't it? So what the mechanical engineers did is they designed a filter in a mechanical way. That's it. So and they can damp down, well, more or less, and a specific filter, because you have the resonance frequency, you have friction, and you get a spread of frequencies which are damped, and others are not damped. So, of course, the low pass is important, the pass filter is important, because you want to produce energy for your oven, remember? You want to put pizza. If you have just a high pass filter, wouldn't be so effective because then you won't get any current at your oven. But so you need some filter which is both to a low pass filter or damps down the frequencies which are critical to your mechanical infrastructure. And these are done by this wall, just filters putting some frequencies out of it. Well, you as an electrical engineer know more difficult filters, right? So like the Chebyshev filters and others, which are much more efficient, isn't it? And you know methods how to design these filters in an optimal way. You want this population I think, in signals and systems and other lectures, where you have methods for it. And this is wonderful. Now you have the design rule for how to design this kind of filter. Now the story at the very end. Well, this is the mechanical version. By the way, these kind of filters exist in practice, not just in electrical, energy generation, but also in cars. If you have a motor, whatever EV or combustion engine, which is at the front, and you have a rear-wheel driven car, you have the very same. You have a shaft in between, and while there are people who are driving that way, push the pedal, and then you have a step, and this produces oscillations. And there are cars, like one of the older Mercedes, which if you push the pedal, so the gas pedal, you get so much oscillations, you're oscillating back and forth because you're rotating the shaft, so it goes that way. It's a little bit strange. By the way, this car is called Bonanza car, that way. And there you can use some sort of such a filter in between in a mechanical way. My colleague Thomas Leibniz said, well, yes, mechanics, well, it's stupid because there are just exactly one frequency I can cancel out. That's difficult. Why not take the generator and attach additional power electronics to it and drive the generator that way, that the generator cancels out the frequencies. And this works also. You can do generator frequency damping, generator-based frequency damping in that way. And well, I'm worrying about the mechanical guys. So he had the electrical engineers have also a problem because he forget that his generator has to produce counter forces in the mechanical objects on the ground. And you need to fix the generator in that way. And then he did his experiments in his hall over here. And it worked well for some seconds. And after a while, the generator flipped out of the ground because it's oscillating, and the fixture to the ground broke. Well, yeah, that problem, you have to ask the mechanical engineers how to fix the generator correctly such that I can produce the counter forces. So that's it for that. And 3 minutes in fast forward there. Well, let me give you a second example, which is a hydraulic mechanical cylinder, which everybody has if he drives cars or has a wonderful bike with hydraulics, which also works that way. So, you know, if a hydraulic, you have the following situation: you press your brake pedal, you have hydraulics transported to the brake discs. If you have just one pipe, and this pipe bursts, you really have a problem if you drive 130 or 180 kilometers per hour. Therefore, in every car in the world, you have two pipe systems, so redundancy. And here is the structure how this works. Well, here's your feet. You press on the pedal. There's a cylinder, it's called main cylinder in the car. And here you have some sort of a shaft, and again the cylinder moves hydraulic liquid. And on the right hand side you have the very same. Here are reservoirs just putting all this liquid into this cylinder structure. That's it. These two pistons are coupled wire springs to the environment, but also in between the first one and the second. What happens if you press both? The spring is still. Both elements move towards the right hand side, right? So everything which is transported here is transported there, it moves here, down through a pipe system, and then you get the force on the other side, right? So what happens if you have a hole in the liquid pipe over here? Then the liquid pours out, so it falls down, but the force remains, right? That's it. So that's a working principle. And what I want to do here is to model this with the electrical equivalent circuit modeling, which is done here. I don't want to do it explicitly. You find a lot of gyrators putting force velocity into pressure and flow, volume flow. Then again, force velocity into pressure, volume flow, etc. On the right hand side, you have the various side. And in between, you find liquid pipes. And if you put them in between, you find in the hydraulic domain a capacitor, the pipe itself, and that's it. So here you find the hydraulic domain. The mechanical domain is given here. So this is something for your homework to find out which element corresponds to what element here in this mechanical drawing. This is perhaps something that's more complex, and you see, well, this is something which you know as an electrical engineer you should not hear of, seems simple, but now you have two domains, the coupling elements in between, and you should look to find just to attach each element to the object or the electronic objects. With that, I stop here. See you tomorrow. Have a good time. Bye-bye.